Hello everyone, and welcome to YouTube. Today we're going to be discussing a very interesting fluid dynamical problem, impacts at free surfaces. Impact problems are one of the most common ways we regular people interact with fluids, because everybody's seen rain before. These impact problems can be roughly classified into two types, impacts by rigid bodies and impacts by droplets. Understanding these impacts are critical to getting to the underlying physics in inkjet printing, icing of planes, soil erosion, combustion, spray cooling of nuclear reactors, and many, many other interesting applications. Generally speaking, this problem is very complicated. As the interface after impact can take on a variety of different geometrical shapes that are quite hard to describe using pure mathematics. So what we normally do is we turn to experiments to get information about this phenomenon. Our journey to the study of the physics of these problems starts with this man, Arthur Mason Worthington. He was born on the 11th of June in 1852 in Manchester, England. He's best known for his work in the physics of splashes. He was a pioneer in using high-speed photography, and his most well-known work, A Study of Splashes, was published in 1908. This image here is from that book. Surprisingly, I can't find a single picture of this man. I can only find pictures of the other Arthur Worthington, who lived during the same era, who was best known for being an alternative religious leader in Australia and for having too many wives. So let that be a lesson to everyone. If you want to be famous and have your picture all over the internet, don't be a physicist. At the time, limited ability and experimental techniques hindered the growth of this field, as sound theoretical predictions are hard to come by for this particular type of fluid flow. However, advances in technology and the refinement of the high-speed camera has allowed for many more studies of this very interesting interfacial phenomenon. In our video, I'll give you some background info about how physicists and engineers study fluid flows, and then show you some videos of impacts taken with the high-speed camera, much like this one depicted here in the Harris lab at Brown University. A long time ago, two very smart guys by the name of Navier and Stokes invented this equation which describes the motion of fluids. Essentially, this mathematical statement is equivalent to Newton's second law that we all know and love, but for fluids, the force is equal to the mass times acceleration. The left-hand side of this very fancy equation is the mass times the acceleration, and the right-hand side is the forces felt on the fluid. Part of what makes fluid dynamics so complicated is this convective term that appears on the left. Convection is generally defined as the transport of a substance by bulk motion. In other words, if we imagine a large amount of fluid as the superposition of many small elements of fluid, convection essentially means that these small elements are free to move around and swap places with other small elements. This does not happen in solids. As a result, the motion of fluids is what we call nonlinear. This gives rise to the chaotic behavior of fluid motion, also known as turbulence. In order to get theoretical predictions for these impact problems, we would have to solve this equation with the correct conditions at all times. Exactly. Generally, this is impossible. No, I'm serious. Literally, no one knows how to solve that. It's actually one of the Millennium Prizes in mathematics. And if you can prove that there's a unique solution at all times, well, you're automatically a millionaire. So, what do we do when we can't exactly solve a problem? Well, we turn to experiments to see if we can identify some relevant physics. So, these impact problems depend on many different physical quantities, like object size, object speed, fluid density, fluid surface tension, fluid viscosity, etc., etc. Luckily, there's a mathematical technique we use to reduce these many quantities into just 4 variables: the Reynolds number, the Weber number, the Froude number, and the dimensionless length. We do this to decrease the overall complexity of our problem. The Reynolds number is simply the ratio of inertial forces, so you can think, for this problem, drop size or drop velocity to viscous forces. The Weber number is the ratio of inertia to surface tension, and the Froude number is the ratio of inertia to an external field, which is almost always gravity. In studying the physics of the impact, we only really need to consider the Weber number and the Reynolds number. Essentially, these two quantities cover the entire parameter space, and if we vary them, we can determine the effect that all those different physical quantities have on the problem. In this video, we'll start by talking about a rigid object impacting a free surface. The following video was taken at the Harris Lab at Brown University. Here we have a small nylon sphere impacting on a still water bath. As the sphere impacts the free surface, waves are generated and propagate radially outward from the point of impact. As the sphere continues to translate down, a cavity is formed, and due to inertia and surface tension forces, that cavity collapses. As that cavity collapses, a small jet of fluid called a Worthington jet forms, and sometimes small droplets get ejected from that Worthington jet. I'll play it again here so you all can see what's happening. You see that small little drop get ejected off the Worthington jet? That's commonly referred to as a satellite drop. If we continue to increase the inertia, so higher Weber and or Reynolds number, we can get even more complicated shapes, and eventually we'll get splashing, which is depicted clearly in the motion picture The Sandlot from 1993. Now let's talk about droplet impacts. Because the physics of the interaction is slightly different, you get slightly different phenomena. There's a regime in the limit that the Weber number is small where the droplet actually bounces. So what happens here is that a small cushion of air gets trapped between the droplet and the liquid interface, and that air cushion acts to prevent droplet coalescence. If we increase the Weber and or Reynolds number, the drop will begin to behave more like the rigid body case, where a cavity is formed and a subsequent Worthington jet is generated. If we continue to increase the droplet inertia, you'll get large cavity formation and eventually splashing. So thank you very much for watching my video. I hope you all enjoyed it and hopefully learned something from it. See you next time.